Hi everyone, welcome to another tutorial on LSED. In today's video, we'll explore the link between the central limit theorem, something we covered in the last video, and the null hypothesis significance testing. I know that's a lot of different words, however, don't worry, we'll get around to it. Now, the null hypothesis significance testing is what you commonly hear about as hypothesis testing. So usually when somebody says hypothesis test or hypothesis testing, what they are actually referring to is the null hypothesis significance testing. For those of you who are mathematically inclined and would like to understand this better, remember that there can be different types of hypothesis tests, and feel free to look up Neyman-Pearson paradigm of one hypothesis test. So what we will look at and explore is basically the Neyman-Pearson paradigm of hypothesis testing. So why should you know about hypothesis testing? Why is it useful to you? How will you gain from learning about hypothesis testing? So hypothesis testing has enormous applications in business, in science, in management, in decision sciences, in machine learning. It's a solid technique for practicing statistical inference theory. In other words, using data to understand the distribution that generated it. It's a common component of using statistical models to understand data sets and make inferences from it. Moving on to the sample means distribution. So last time we talked about the central limit theorem. The basic essence of the central limit theorem is that regardless of any distribution that you begin with, it doesn't matter if the distribution is normal or not. It can be any distribution, but if you start taking samples from that distribution, random samples, that's very important, random and independent samples from that distribution, and start computing the means of those distributions. As the number of data points in the sample increases, you will notice that these samples start taking on the shape of a normal distribution or a normal curve, a Gaussian curve. And that's a vital piece of information. This is generally a universal phenomena and is extremely useful in statistical inference theory, as we'll see. What you see on the screen right now is a representation of different types of shapes, different types of distributions. So you have the exponential, the uniform, the parabolic, and the normal as well. And what you will notice is that as you start taking a higher number of data points within your samples, the shape of the distribution of the means of that sample starts to take on a distinctly bell-shaped or a normal distribution curve shape. This is especially true once you start increasing the size of the sample to 30 or greater than 30. So sample means parameters. So as we've discussed before, that there is a difference between the concept of a parameter and a statistic. Just to refresh our minds and memories about this, remember that when you're dealing with the entire population, so if you're dealing with the entire data set and calculating a metric for the data set, that is usually referred to as a parameter. On the other hand, if you just take a small sample and from that sample you derive that metric, the purpose of deriving that metric is to then estimate the metric for the entire population. Then the right terminology for that would be statistic. So that is a key difference to bear in mind. So what you see on the screen right now is we have a distribution mentioned in column B. So you have these numbers here all the way from 82, 71, 35 all the way till 41. It's just a randomly selected set of numbers. So when we look at this distribution, and in our case right now, this is our entire population. So what is the mean of that population? You already know that you can calculate the mean of that population by using the Excel formulas around average. And then you can also calculate the standard deviation of this by using this Excel formula of STDEV. Please make sure you use .p. The .p here signifies the fact that this is the entire population. This is not a sample. This is the entire population right now. So if you go ahead and select the stdev dot p, and then you make selection of the entire data set and close the brackets and compute it. There you have the standard deviation of this population. Now, let's say that we start taking samples from this population two at a time. So if we take samples from this population two at a time, remember that how many different ways can we do this in? Since we have a sum total of 6 points in this, so if you were to randomly select any two data points from this entire population, so there is 6 times 6 or 36 different ways that you can do that. You can select the first data point in 6 ways, and you can again select the second data point in 6 ways. So what you have in column M and N is the enumeration of all of those possibilities. So as you will see, there are 36 possibilities. This is the first data point and this is the second data point. So let's go ahead and take a mean of the samples two at a time. So you know very well that once we start taking the means, regardless of what the original distribution was, here you can see the graph on the left hand side shows you a random compilation of points, no specific shape to this distribution. But once you start taking the means of the samples of this distribution, it's anybody's guess now that we know that due to the central limit theorem, what we'll notice is it'll start on taking some sort of a Gaussian or a normal shape. So let's go ahead and compute this. If we were to take the average of these numbers, and there we are, we have the means for all the possible samples, all the 36 samples, we have the means. Okay, so now that we have the means, it is important to understand that these means by themselves also have a mean. So if my distribution is this set right here, so we've calculated the means, and let's just highlight it. So if this was my population, the colored cells, if this is my population, then what is the mean of that population? So what you will find is, if you calculate the mean of this, and let's do it here, let's just do an average of these numbers right here, you will notice that surprisingly enough, the mean of the mean of samples is equal to the mean of the actual population. And this is a very important result for multiple reasons. So, and we have, remember that we have taken the samples two at a time, but if you were to replicate this with taking 3 or 4 or 5, depending upon how large your population is, if you practice this in Excel yourself or in any software yourself with samples of different sizes, so calculate all the samples of, let's say, size 3 or size 4 or size 5, and compute the means of those independent samples, and then take the mean of the distribution of those means, you will notice that it always equals the mean of the entire population. Now, what about standard deviation? So let's say we were to calculate the standard deviation of this entire population right here. So let's go ahead and calculate the standard deviation, and we see that the standard deviation is 12.35. Well, this is not equal, right? The standard deviation of the means of samples is not equal to the standard deviation of the population. However, there is a relationship, and the relationship is that the standard deviation of the means is always going to be equal to the standard deviation of the original population, which here is 17.46, divided by the square root of the size of samples. Now remember, the size of samples here is 2. We're taking 2 data points at a time in each sample. So if you wanted to compute this, what you do is you take the standard deviation of the entire population and divide it by the square root of the size of the samples. We are taking 2 at a time. So square root of 2. And you will notice that it is now giving us the same result. So this is an important relationship that we just looked at for the means of samples. So the mean of the means of samples is always equal to is always going to be equal to the mean of the entire population, and the standard deviation of the mean of samples is going to be equal to the standard deviation of the entire population divided by the square root of the size of the samples, which in this case was 2. But this result holds true regardless of what your size of samples are. The only caveat you have to bear in mind is make sure that you enumerate all possible samples that you can take. So for instance, if we were to do this exercise with 3 data points per sample, remember that for the population size of 6, that would mean that the first data point can be selected in 6 ways, the second data point can also be selected in 6 ways, and the third data point could also be selected in 6 ways, giving you a total combination of 216. Instead of the 36 combinations that you see here, you would get 216, and then you will have to compute first the mean of each of those samples, and then if you replicate the computation of the mean and the standard deviation, you will see that the result holds true. Okay, so this result will be useful to us when we proceed to further topics. So this is what we just discussed. This is just the key insight that we just looked at from the previous sheet. So the mean of the population is going to be equal to the mean of the means of samples, and that is what is written here mathematically. The P here refers to population. The X bar here refers to the fact that we are taking the means of the samples. This is the second result in regards to standard deviation. So the population standard deviation divided by square root of the sample size will give you the standard deviation of the complete distribution of the means of the samples. Okay, so let's extend this idea a bit further. Let's think about this question here. So the question says that if a coin is tossed 100 times and we make a note of the number of heads that we get with each sequence of 100 tosses, what do the results tell us about the fairness of the coin? The results are listed from column L till column N, as you can see here. So if you think about it, if you have a coin, and that to a fair coin, fair meaning that there is equal probability of us getting a head or a tail, the quantity of metal, let's say, is evenly distributed across the coin, and it's a fair coin. And if that's a starting idea, if our starting idea is that we have a fair coin and we toss that coin 100 times and we make a note of the number of heads, what do you expect from a fair coin? So for many of you, or for most of you, the answer will be that the number of heads will come very close to 50. So if it's a fair coin, there is equal probability. We generally expect to see around 50 heads and 50 tails, right? And so if you toss 100 coins and you get 50 heads, you will say, yeah, this certainly looks like a fair coin, or a very fair coin for that matter. So the certainty of fairness in this case, right? In fact, not certainty, it should be the uncertainty. The uncertainty of fairness is low. You're expecting it to be a very fair coin. If you were to repeat the exercise again, do another 100 coin tosses, and this time the number of heads is 55. Well, is this still a fair coin? Sure, because you know by experience that it will not always be exactly 50 heads. It will slightly vary, right? So even with 55 heads, it looks like a fair coin, yeah, reasonably fair coin. So again, the uncertainty of fairness is low. We are fairly certain. In other words, we are fairly certain that this looks like a fair coin. Okay, repeat that exercise again, and this time you get 45 heads. Well, it still kind of looks the same. You know, you could get slightly higher than 50 and slightly lower than 50. So this still looks like a fairly, we are fairly certain that it's a fair coin. However, look at the next corresponding two entries. Let's say if you were to toss 100 coins, or rather toss the same coin 100 times, maybe not 100 coins, and let's say you get 90 heads out of those 100 tosses. Now, would you still feel that this is a fair coin? Probably not, because it's unlikely, highly unlikely that you toss a fair coin 100 times and you get 90 heads. I'm not saying it can't happen, but the possibility of that happening is extremely rare. And now, also you would have a certain degree of doubt in your mind whether it's a fair coin or not. You will start questioning the certainty of this, or rather you will be highly uncertain of its fairness. Put another way, if you toss the same coin 100 times and this time you get the other extreme, which is the number of heads is only 10, well, there is again, justifiable reason for you to be now suspicious of the fairness of the coin. You will probably say that, yeah, this seems to be biased towards giving us tails, because the number of heads is just too small. So again, your the uncertainty of fairness is going to be very high. So within the null hypothesis significance testing, this is one of the key precepts that you have to bear in mind, that when there's a certain set of events that you're repeating again and again, and what your starting idea is, but then if you start getting extreme values for those repeated events, you'll start to question whether your starting idea was correct or not, right? So this is one important thing to understand and bear in mind about the significance testing that we are looking at. So with that at the back of our minds, let's go on to the next thing that we want to understand. So here what you have is a graphical representation of the same thing that we were discussing on the previous page, which is if you were to toss a fair coin 100 times, if it is in fact a fair coin 100 times, you would expect that almost about 50 of those 100 tosses will give you heads. Not always going to be the case. There'll be some variance. Some of these will give you more than 50 and some will give you less than 50, which is okay, but it's kind of centered around getting 50 heads, and that's what you see in the graph on the left hand side. Now the same thing can be represented in terms of z-scores. Now if you recall from one of our previous videos, what exactly is a z-score? A z-score is nothing but seeing how far a data point is from the average, from the mean, when represented in terms of standard deviations. In other words, how far is a point in terms of standard deviations? Is it 1 standard deviation away? Is it 2 standard deviations away? Is it minus 1.7 standard deviations away from the mean? That's what a z-score represents, how far a point is from the mean when measured in terms of standard deviation. So we can represent the same distribution that you see here on the left side in terms of z-scores. As you can see, it retains the same shape, right? And it's kind of and it is going to retain a very Gaussian curve, a normal distribution like shape, provided you are doing enough samples of this. So with this, what we now have to understand is that at what point shall we start entertaining doubts of fairness? If you recall the previous page, we said that, yeah, if I get 90 heads, then I'm going to be highly uncertain of the fairness. If I get 10 heads only, again, I'll think that this is not a fair coin because it is tail biased. So this one will be head biased and this one will be tail biased, right? So how do we decide what is that point beyond which we will say, or we can say that, yeah, now I'm suspicious enough that this is not a fair coin? So there's no one single answer to it. However, the answer comes from the fact that what level of error are we willing to accept? So for instance, if I say, and this is what you'll generally see, if I say that, yeah, in 5% of the cases, I'm willing to accept an error, which is to say that as long as I'm correct 95% of the times, it will work for us. That's a working model. We can be pragmatic or practical and say that, yeah, with 95% of the cases, if I'm fine with it, then I'm good. So that can be one way by which we can go about deciding that point beyond which we'll then start to question our basic idea of fairness of the coin. Okay. So there are two key concepts here. One is the concept of uncertainty, and the second is the concept of acceptability, or the acceptable error margin that we want to keep in our statistical model. So basis these two concepts, what we can now is tie this together and understand that for the distribution of the tossing of coins, we will have to select a point which represents a point that represents 95%, and the other half will be the remaining 5%, right? That remaining 5% is the error margin, or the acceptable error that we are fine with. So when we look at hypothesis testing, especially the Neyman Pearson hypothesis testing that we're discussing today, this is known as level of significance. The level of significance is nothing but the amount of error that we are willing to accept within the model. So let's say that the amount of error we are willing to go ahead with is 5%. We want the model to capture 95% of the inferences accurately. Okay, so this is the level of significance. And then the cutoff point beyond which we will then start to be suspicious of the results. The fact that the result shows that our basic opening idea was incorrect is known as critical point. So less than the critical point, we'll be reasonably certain that our basic idea or our starting idea was correct. Beyond the critical point, we'll start to question it, and we will reject the starting idea. This, guys, is the essence of the null hypothesis significance testing. Within null hypothesis significance testing, there is a certain point that we decide on. That point is the critical point. If your sample gives you a result beyond that critical point, which is either to the right or to the left of that critical point, towards the extremes, then you would say that, yeah, let's reject the starting idea. On the other hand, if you get a result from your sample which is lower than that critical point, then you can say that we are unable to reject the starting idea. That's all that there is to hypothesis testing. So it's a very simple concept, but when you do understand the central limit theorem and why hypothesis testing works in inferential theory, that makes the concept much more clearer to us. So let's extend this a bit further. This is the same distribution diagram of 100 tosses of a coin, and it's just color coded. It's the same thing as the last graph. So here, remember that we said that we are fine with the acceptable error as being 5%, right? So the level of significance, which is what the acceptable error in this hypothesis test for us is. So let's say the level of significance for us that we are fine with is going to be 5%, right? So what does it really, what does this really mean for us? So what it means is that somewhere on this, we will have to make a cutoff point to represent this 5%, right? But if you notice the diagram, you see there are two red colored cutoff points. There's not one. The red bars represent the cutoff points here, but there isn't one, there is two. Now, why is there two? Now, the reason we have two cutoff points in this example specifically is, remember, the original question says, what do the results tell us about the fairness of the coin? So remember that the coin can be unfair in two ways. See these two results in amber right here? So a coin that is head biased is also unfair, and the coin that is tail biased is also unfair. In other words, if I get very low values of heads, or very high values of heads, then I can call the coin as unfair, or I can infer that the coin is unfair, right? So basically, that 5% significance level that we were talking about, that 5% acceptable error in the model that we are talking about, is broken up into two parts. One part is for extremely low number of heads, and the other part is for extremely high number of heads. So in other words, this 5% is now going to be broken up into two halves, each of them with 2.5%. And let's say this is the higher extreme values, and then you have 2.5% of the lower extreme values. So if you look at the diagram here, this section right here, and let me just make a quick arrow so that it's easier to kind of understand. So this section that you see on the diagram represents the higher end of the extreme values, the 2.5%. And then similarly, what you see is that for the lower end, which is this part right here, represents the lower set of extreme values, the 2.5%. So that's why you have two areas, and these areas are known as areas of rejection. So what are we rejecting? Remember, there's a basic idea that we've started with, that the coin is fair. So if our sample gives us a value in these two areas, of rejection, then what we do is then we reject the starting idea that the coin is fair. Okay. Now, why did we select 5%? Remember that the 5% is one of the two common values that you will see in null hypothesis significance testing. The other value that you will see sometimes is, we can say that, okay, I just want to go ahead with the level of acceptable error as 1% in our observations, in which case your level of significance can also be 1%. You can choose that basis the sensitivity of the statistical analysis that you're doing, which is if you're doing an analysis where accuracy is of extreme importance because you're dealing with a subject, let's say, which has a lot of money involved, or let's say there are other costs like people's lives or public health and so on, then in that case you can definitely go in with a level of significance of 1%, which means the acceptable error rate you are taking in is just 1%. Otherwise, generally what you'll see is for other fields or for most of the fields, you'll see the level of significance is generally selected as 5%. So understand this key concept that you have critical point. In this case, you have two different critical or cutoff points. Beyond this, to the right and to the left, you have areas of rejection. Okay, so another key concept to bear in mind. Okay, so let's look at something else. So here you have three different diagrams. So here you have three different diagrams. So the first diagram that you see on the left hand side is what we were seeing on the previous page. So this is an example of conducting a double-tailed hypothesis test. A double-tailed hypothesis test. What is a double-tailed hypothesis test? A double-tailed hypothesis test is one which has the rejection area broken up into two smaller rejection areas, one on the right extreme and one on the left extreme. An example of this is the coin toss example that we just looked at. So remember that when you're checking the fairness of a coin can be unfair in two ways, depending upon whether it is tail biased or whether it is head biased, right? So the entire rejection area of 5% is broken up into two smaller parts, one on each extreme. So this is a double-tailed test. But you can also have a single-tailed test, and these single-tailed tests can either be left single-tailed or it can be right single-tailed also. So what do we mean by that? So let's say that our starting idea is that the height of boys in a certain city is greater than 180 centimeters. Let's say that's our starting area, that the height of boys in a certain city is greater than 180 centimeters. Okay, so in this case, you don't have to test one side of this assessment. Okay, so basically you just have a single tail test, or let's say your starting idea is that for a certain courier service, their delivery time is always less than 48 hours. So again, remember that in this case, the only way that you can question this starting idea is when is when the delivery time exceeds 48 hours, right? You are just testing one side, which is the delivery hours greater than 48 or lower than 48, right? So this is again another example of a one-tailed test, right? So whenever we are checking equality, it will generally be a double-tailed test. Whenever we are checking greater than or less than, these will be single-tailed tests. So therein lies the difference between when do we use a double-tailed test and when do we use a single-tailed test. Okay, so now to extend this idea further, remember that when we are talking about a double-tailed test, we said that our rejection area is 5%, right? So let's just mention it. So our level of significance. So let's say our level of significance is 5%. Let's just shift it here. And since the level of significance is 5%, what does that mean? It means that the amount of error or the acceptable error in this case in the statistical model is 5%. Since it is broken up into two smaller parts. So since it is broken up into two smaller parts, so let's say the rejection area that we have. How many rejection areas do we have? We have two rejection areas, correct? One to the left and one to the right. So there are two of them that we have. Let's make sure that we also point towards them just for easier visibility. So what are those two rejection areas? One is this area, and the other one that you have is this rejection area right there. Okay, so there are two rejection areas. What is the percentage of each rejection area? Since the total rejection area is 5%, then each of them, so let's say the right extreme rejection area is going to be 2.5%, and then the left extreme rejection area is also going to be 2.5%, right? Now, how is this 2.5% also written? Remember that the 2.5% that you're looking at, how could this be written? So the 2.5% can also be written as 0.025. Remember, it's a simple thing, converting percentages to decimal points, right? So it can be written that the 2.5% can be written as 0.025 for both the left extreme and the right extreme, right? So if you now go to the z-score table, and look for that specific value that we are trying to get to, right? So where do we have the value in this? So what you will notice when you start looking for these values that you have is, so for instance, let's start off with the negative values on the z-score. Okay, so if you look at the negative values on the z-score, you will notice that remember it was 0.25. So where do we have 0.25 for the first time? So within this table, you will see that the 0.25 shows up on the table. Let me just circle it for easier visibility. So this is 0.03, 0.29, 0.28, 0.27, 0.26. Yeah, somewhere around here. If you notice, it is this value right here. And let's go ahead and just make it more visible. Okay, and no fill there. So if you can see on the screen, we have just highlighted or rather circled a certain value of 0.025, right? Now this 0.025 is 1.9 in terms of, so remember we're looking up the z-score, right? So in fact, if you see this, that this is a closer value, 0.0250. This is an exact value. So this value is 1.96, minus 1.96 on the z-score. Okay, so this is one value. Now, what is the other value? So the other value, to get to the other value, remember that if you take away 2.5%, if you take away 2.5% from 100, so So the left extreme is 0.25 and the right extreme value will then be 1 minus 0.25. Why 1? Because remember, the complete area under the curve for the normal distribution is 1. So if we do that, then it is going to be 0.975, right? So when we look at the z-score, we are going to look at 0.975. So where do we have 0.975? So 0.975. There, you see, there is an exact 0.975 that we have. So this is the other value that we have. Okay, let's select this and there. So where are we getting the 0.975? You'll see it's an exact mirror match. So the 0.975 also happens at 1.9, and if you scroll up and see, this is 1.96. So basically what we have now calculated is we've converted the percentages to z-score. So the z-score of the right extreme, rejection area is what? The z-score of the right extreme rejection area was 1.96, positive 1.96. And then the z-score of the left extreme rejection area, that we've just looked at, is going to be minus 1.96. Going to be minus 1.96. So why is this going to be useful? The reason this is going to be useful is that any point of time when you're dealing with the statistical inference of null hypothesis, whenever you're doing the null hypothesis significance testing, given a sample, if you calculate the p-value, in fact, not even the p-value, let's leave out the p-value. Given a sample, if you just calculate the z-score, of that sample, and if the z-score appears to be, let's say, greater than 1.96 or less than less than minus 1.96. So basically, let's say you have a sample, you calculate the z-score of that sample, and the z-score happens to be greater than 1.96, which is this area, or less than minus 1.96, which is this area, then you can begin to doubt the opening or the starting statement, right? Then you can say, yeah, our starting idea is probably not right. You know, this sample is so extreme. It is so much to the left or so much to the right towards the end of the distribution that now we can reject that starting idea. Okay, and if you recall, that's what null hypothesis is. A null hypothesis is our opening hypothesis or is our starting idea. And if the sample is very extreme, so extreme that it is greater than 1.96 or less than minus 1.96 in terms of z-scores, then we will reject that null hypothesis, or we will reject that starting idea, the idea that we began with. All right. On the other hand, if your z-score falls in between, so if your z-score was this area, this central area that we have, the area that is bounded on the left and the right by these two critical points, then you will say that, you know what, this is more towards the center. We are unable to reject the null hypothesis, or we are unable to reject the basic idea, or the starting idea, the idea that we began with. And again, what are these two numbers? The 1.96 and the minus 1.96 are known as the critical points, as we discussed. These are the cutoff points. The cutoff points above or below which, if you have values for the samples, then we either reject it or we are unable to reject it. Remember, we will not say that we will accept. So this region in between is technically, in some textbooks or discussions, you will hear that this central area that we are looking at, you know, this area, some textbooks will call it the region of acceptance. You know, in other words, if your z-score falls in this range, then we can say that we are going to accept the starting idea or the null hypothesis. This is not how you should generally think about it. I would recommend and encourage that instead of region of acceptance, you still call it region of non-rejection, right? It might look the same, but it does make a difference. So the right way of looking at it is to think of it as a region of non-rejection. And then these two regions are the regions of rejection, as we know. Okay, and the critical points are 1.96 minus 1.96. Remember, we are currently discussing a double tail test. On the other hand, when you think about a single tail test, if you're looking at a single tail test, again, let's say the level of significance is again 5%, right? Which is level of significance, just to recap, is nothing but the amount of acceptable error that you can have in the statistical model for the null hypothesis test that you're doing. Okay, how many rejection areas do you have? You only have one rejection area, right? Either on the left or to the right. So the number of rejection areas is 1. So if the number of rejection areas is 1, so what is the rejection, what is the actual rejection area? So the rejection area is going to be nothing but 5%, right? That's going to be the rejection area. It's going to be 5%. So if the rejection area is 5%, if the rejection area is 5%, right, then remember, in that case, what will be the critical point? The critical point, to look up the critical point, remember that 5% can be represented as 0.05 on the left end, and on the right end it will be 1 minus 0.05, or it will be 0.95. So if you go to the z-score table, and let's start off with this number. The number that we're looking for is 0.95 for the right end of the extremity. So what is 0.95? So let's start looking here. In the center, you see 0.94845, 0.94950, and these 2 points appear to be the closest. You have the 0.94950 and 0.95053, but you see that this is just like 50 points away and this is 53 points away. So the closer point on this is going to be this one. This point is closer. And let's just change the outline on this one, and let's say we select a purple outline. Okay. So this point that we've just circled in purple color represents, what does it represent? It represents this rejection area, the rejection area that you have on the right. Okay, so let's just make an arrow. So this 0.95 is represented by this rejection area on the right. And what is the critical point? The critical point, or the cutoff point, is going to be 1.64. You see the intersection of 1.6 and 0.04 is this number. So the critical point is going to be 1.64. Okay, so let's just mention that. So the critical point, so let's call it the right critical point. So the right critical point is going to be 1.64. Okay, and then what about the left? So for the left, it's 0.05, right? So if we go back to the z-score table, and if we look for 0.05, so the 0.05, let's look for it. So the 0.05 is going to be, so these are our options, right? There is 0.05. And as you can see, the 0.05 again is at the intersection of 1.64 with a negative sign. So that's our second critical point. So the left critical point, if you're doing a left single tail test, so your left critical point is going to be nothing but minus 1.64. So how will this operate now? So basically what it means is, if you're doing a single tail test, And if that single tail test is a left single tail test, then given a sample, if you calculate the z-score of that sample, and if that z-score turns out to be less than 1.64, basically less than 1.64 means it will fall somewhere in this area, then what you can do is you can reject the starting idea or the null hypothesis. Similarly, if you're doing a right-tailed hypothesis test and the z-score of the sample is greater than 1.64, if it is greater than 1.64, which means it falls in this area, this rejection area to the extreme right, then you can reject the null hypothesis. Also, correspondingly, bear in mind, if you're doing a left-tailed test and your z-score is greater than 0.05, so it's basically this central area, right? Then you will say that we failed to reject the null. Then we say that we failed to reject the null. Remember, we will not say that we accept the null hypothesis. We will say that we failed to reject the null hypothesis, right? So again, this is the area that we're talking about. Let me just take this and paste it. Yeah. So this is the region of non-rejection. Okay. Similarly, if you're dealing with a right tail test and your z-score turns out to be less than 1.64, less than this number, the right critical point, then we'll say that we fail to reject the null again, and this is going to be the region of non-rejection for us, right? So guys, this is the key concept behind the null hypothesis significant testing that we do. Okay, we start off with a sample. For that sample, we calculate the z-score. Once we calculate the z-score, then we're going to look at whether it's a double tail test or a left single tailed or a right single tailed test. Depending on that, we calculate the z-score that we've calculated for the sample. We compare if it is above or lower the critical point, and basis that we can then make our inference. Either we reject the null or we fail to reject the null. Again, and I know I've repeated myself too many times on this, but remember, you don't accept the null, you just fail to reject the null. Okay. All right. So moving on. How is it connected to the mean of samples that we looked at? So the way it is connected to the mean of samples that we looked at is that given a sample, we have to calculate the z-score. How will you calculate the z-score? The way you will calculate the z-score is basically given by this formula that you have on the sheet right now. This is the simple z-score formula, which is nothing but the data point minus the mean divided by the standard deviation, right? But in this case, what is the data point? Well, the data point is nothing but the mean of a sample, right? Remember, we are dealing with means of samples. So the data point that you have here, the x that you see here, is nothing but the mean of the sample selected. And then what do you have on the right? On the right, you have the mean of the distribution of the mean of samples. And that's why this is referred to right now as mu and x bar. So because this is the mean of the mean of samples. Remember, we had calculated the mean of samples here when we looked at this example. So this is our list of mean of samples, and we calculated the mean of samples as 53.33, right? So this is what this represents here. This is the mean of samples. Okay, so that's the number here. And then what is this? So this is the standard deviation of the mean of samples. Again, remember, how did we calculate the standard deviation of the mean of samples? So this is given here in this formula. So the second formula expands on the first formula. So you have the mean of the specific sample that you selected for the study. Also, the mean of samples is the same as the mean of population, so we can also write it like this. And the standard deviation of the mean of samples distribution can be written as the standard deviation of the population divided by the square root of the size of the sample. The size of the sample here is n in this case. All right. So this is the formulaic version or the formulation of the test. So given a sample, we calculate this. We use this formula to calculate the z-score. Then we check the z-score versus the critical point, and basis that we can draw inferences. So finally, what kind of problems can we solve? So there are numerous problems, estimation problems that you can solve using the null hypothesis. This is just an example of the sort of questions that you can solve. Obviously, you can do much more complex stuff also, but in essence, this is what we try and do. So look at this question here. It says that a town's municipal corporation says that the height of the girls in the town is 165 centimeters. This is our null hypothesis. This is our starting idea or opening idea, right? And this is the idea that we have to test. Now, from historical records, we know that the standard deviation of the height of girls in the town is about 20 centimeters. And then the height of 20 girls has been selected randomly and is found to be 162 centimeters. So basically, we select a sample of 20 girls from the town. We check their heights, and basis their heights, we surmise, in fact, not surmise, but we calculate that the average of the height of those 20 girls is 162 centimeters. So basically, what does it mean? It means the sample average is 162 centimeters. And then, if given the level of significance of 5%, we have to test the claim of the municipal corporation that the height of the girls is 165 centimeters. So this is a very useful thing now, So remember that a town might have thousands or hundreds of thousands of girls, depending on whether it's a town or a city. If you have to estimate the height of the girls in that town, you can't possibly go to everybody and ask them their height. It will not be logistically possible. So the closest that we can do is we can make an estimate. How will we make that estimate? We'll do a sample survey. So we'll randomly select 20 girls and check their height, and basis that sample or the average that we get from the sample, now we can do the statistical test that we just looked at, or the null hypothesis test. So given the average height of those 20 girls from the sample, we can then calculate the z-score of that sample. And once we have calculated the z-score of the sample, we will then check if the z-score that we have found is greater than or less than the critical point, right? Any guesses as to what kind of test will this be? Will this be a double-tailed test or a single-tailed test? Well, the answer is this will be a double-tailed test. Remember that any point of time when we are checking for exact equality, if you're checking for exact equality, then it will be a double-tailed test. If the basic idea was that the height of the girls in the town is greater than 165 centimeters or less than 165 centimeters, then we would have gone in for a single-tailed test. In this case, it will be a double-tailed test. We'll calculate the z-score. And then we'll check if the z-score is, we'll check the z-score versus the critical points, which is your 1.64, if I recall correctly. And if that is the case, then basis that we'll be able to then make our deductions, draw our inferences of whether we can reject, if we can reject the basic premise that the height of the girls is 165, or whether we will fail to reject the premise that the height of the girls is 165 centimeters. So that's how this will work, and we'll look at it in detail or work out some examples in the next video, where we'll try and understand this better, look at some examples to work this out. One last comment before we close the video for today. Remember what we have looked at today in terms of the null hypothesis significance testing is generally referred to as a z-test. In textbooks or discussions or articles, this is when somebody says, when somebody talks about a z-test, this is what they're talking about. Okay, there are more parts to it that we have to look at, but I would want to leave you with that idea. It's still not complete, but it's an important foundational concept. All right, so that's all that we had in today's video. Hopefully you'll be able to understand the importance of the hypothesis testing technique, and hopefully something to take away from this conversation. Thank you so much for watching. See you next time.